Bismillahirrahmanirrahim. Respected teachers, Assalamu alaikum. My name is Muhammad Umar, and on the behalf of my group members, I would like to present our CEP, that is Complex Engineering Problem, and the topic is Load Profile Analysis and Generating Station Design. First of all, I would like to acknowledge Dr. Amreen Sultana, who gave us the opportunity to complete and work on this project. And nextly, we are also pleased to mention the names of Sir Adnan, Assistant Professor, Department of Electrical Engineering, and Madam Arjuman Samad, Assistant Professor, Department of Electrical Engineering, who, along with Dr. Amreen Sultana, taught us this course, Power Generation EE 411, so that we'll be able to complete this CEP. Now let's get started. We have shown all the load profiles that we have collected from the different research papers. We have also shown the references. We have also given the references of these load profiles. What we have done with these load profiles, we use the MATLAB App Designer tool to make the application so that user can easily access the GUI interface and can easily determine the technical and economical parameters. The technical parameters that we have discussed, that we have calculated from these load profiles are concluded in the given table, that is average load, peak load, base factor, base load, that is actually base load. There is a mistake over here, that is base load, load factor, and energy in kilowatt hour. All these technical parameters of the 10 load profiles are given in the table and also in the app designer as well. I will also give the demo of the app designer shortly, but first of all let me complete the presentation. The interface of our app designer is somewhat like that, in which we have made the 10 different buttons for 10 different load profiles. When the user clicks any of the button of the load profile, then the particular load profile will appear and user can easily access the technical and economical parameters. Okay, the functionality is shown over here. When user click any of the load profile, then what he or she will see is that there are 4 tabs. That is, number 1 is technical tab, economical tab, load curve, and load duration curve. Next, what we have done, Dr. Amreen Sultana asked us to select the 2 worst scenarios among the 10. So according to the load factor, the worst scenario will be the one whose load factor is very low. So you can see over here in this graph that the load profile number 4 and load profile number 7, these 2 load profiles are that whose load factors are very low. So what we have done, we have selected these 2 load profiles, that is load profile number 4 and load profile number 7, so that we can start our designing. For these 2 load profiles, we have suggested the hydropower plant designing for the load profile number 4 and diesel power station designing for load profile number 7. Now let's go through the designing of hydropower plant. And as seen in the table 1, that is, the table 1 is the one that I have shown you in above. The average load is this and maximum demand is this. In order to fit the load curve, we are suggesting 3 generator units. Now we have come to the designing parts, and what we have done, we are going to suggest 3 generator units for this particular load profile, that is load profile number 4. Let me show you load profile number 4 in the, that is actually load profile number 4. We have suggested hydropower plant designing for this particular load profile. And let me show you load profile number 7. This is basically load profile number 7, and we have suggested we will be suggesting diesel power plant designing for this particular load profile. Now let's get through the designing part. That is, number 1 is hydropower plant designing, that is actually the load profile number 4. We are suggesting 3 generator units, one having capacity 50 megawatt and 2 having capacity 500 megawatt. In order to maintain the reliability, the reserve generator would be having capacity of 500 megawatt, so that makes the plant capacity equals to 1550 megawatt. Next thing that we should do is to set the operating schedule for this design. Operating schedule that we have done according to the load curve is given in the table. And next, what we have done, we have calculated plant capacity factor and plant use factor. The plant capacity factor is calculated to be 30% and the plant use factor is calculated to be 79%. Now, since we have suggested 3 generator units, so there must be 3 turbines, which will also make the design of hydropower plant, which makes our design of hydropower plant is of cascaded reservoir. Since there are 3 turbines, so the reservoir are connected in cascaded manner. Consider each reservoir having a head of 100 meter. Acha. Now we have to design the now we have to present the turbine design and penstock design and reservoir design. Since we are suggesting hydropower plant, so these are the components, these are the main components that included in hydropower plant designing. So in order to design the penstock and turbine, what we have need is we want some site data, and the most important site data includes the head, and number 2 is flow rate. So according to M.V. Deshpande, actually 25 to 30 years site data is required, but since for the purpose of this project, as far as this project is concerned, we are assuming the fictional values of head and flow rate, so that but the calculation behind these values are real and can be done on any real value and can be done on any real time data. Okay, so for this project we have only considered the fictional data, but this calculation and the design that we have presented in our project can be extended to the real world solution if we have the real time data. Okay, so let's get through the design. If we are considering 100-meter head, according to M.V. Deshpande, Francis turbine must be selected for this head. So number one thing that we are suggesting over here, that we are suggesting Francis turbine for the hydropower plant for rotating the generator actually. Next, we have calculated different turbine parameters. Since we are suggesting the Francis turbine, so we have to calculate the different parameters that turbine must possess. The parameters, we have calculated all these parameters by using some particular formula and by using some particular method, but according to the head and flow rate, these values comes out when we use the formula for different parameters, just like specific speed, actual speed, nominal diameter, draft tube inlet, and width of distribution. So these are the specifications of the turbines that is connected with 500 megawatt generator, and these are the specifications of turbine that is connected with 50 megawatt generator. Okay, next we are going through the design of generator. Obviously synchronous speed, number of poles, capacity of the generator, voltage level, and frequency. Okay. The next thing that we are also need to consider is that turbine design and turbine type also depends upon the flow rate of water. Actually, I have told you previously that according to M.V. Deshpande, I have also given the reference over here. You can see over here that design of hydropower plant requires the stream flow data and mean annual rainfall data of about 25 to 30 years. Actually, we do not have so much data. So what we have done over here, that we are considering only the fictional data, so that we can present our design for the purpose of this project. Okay, so next thing that we are also need to consider is the FDC, that is flow duration curve. What we need to do is, by using flow rate, flow duration curve is plotted, and turbine must have to be fit on FDC, just like generating units must have to be fit on load curve. Similarly, the turbines that we are selected over here must have to be fitted on the FDC. So you can see over here we have fitted the 3 turbines that we suggested. These 3 turbines are shown in the figure: turbine 1, turbine 2, and turbine 3, and this is the FDC flow duration curve available for the particular site. Okay, next we are going to discuss the design of penstock. All the calculations are given in appendix B. We have done this calculation by using some formula or some methods obviously given in our books, and the results are summarized over here: that length of pipe, material of penstock, diameter of pipe, thickness of pipe. Okay, next thing that is also important is, between the turbine and reservoir there is a surge tank which is used to increase or decrease the pressure in water. So we are also placing the surge tank which is placed between turbine and reservoir. What such tank is actually do? It will reduce or increase the surges in the pressure. Actually, whenever the load reduces on the generator, then generator speed will increases. So what we need to do is we should control the pressure of the water. So what actually such tank is do? It will control the pressure of the water, and if the load on the generator side is increases suddenly, then we need to increase the speed of the generator. And what such tank will do in this situation? It will increase the pressure of the water, so that speed will increase in order to provide the particular frequency. Acha. Next thing is costing of hydropower plant. Again, the all details of costing and the complete calculation is given in appendix B, but the results are summarized over here. The total cost would be this, and cost per kilowatt hour is 6.2 paisa per kilowatt hour. Since we all know that hydro is the renewable energy, and it is the cheapest source of energy among the all, so we can also see over here that the price is very low as compared to other designs. Okay, so that is the design of hydropower plant. Next we will discuss the design of diesel power plant designing. The load profile that we have selected for the diesel is load profile number 7. I have shown you previously this load profile. The average load is of this load profile is this maximum demand. And so what we have done, we are suggesting actually 3 generator units. Again, one having capacity 390 kilowatt and two having capacity 220 kilowatt. So I think you can see over here that the load is given in kilowatts. That's why we are selected diesel power plant designing, but not another type of designing, that is a steam based or gas turbine based, because the load is very low. We have also a reserve generator that is having a capacity of 390 kilowatt, so that makes the plant capacity equals to 1220 kilowatt. The operating schedule for this design would be summarized in the table below, and the plant capacity factor and plant use factor is calculated to be 33% and 86% respectively. Now let's discuss the design of diesel engine and alternator design. Again, the complete design and the calculation is given in appendix C. We are also summarizing, we just summarize the results of the calculation in the table below. What we have done is actually we have suggested 3 generator units, so there must be actually 3 diesel engines that will supply 3 alternators. So there must be 2 diesel engines having capacity 220 kilowatt that should supply the capacity 220 kilowatt, and one that should supply the capacity of 390 kilowatt. So the design parameters of these 2 diesel engines are given in the table, that is engine characteristic, what type of engine it should be, how many strokes we are going to suggest. Engine capacity is this. We are also considering the supercharging generator, number of cylinders for these 2 generators, capacity of each cylinder, diameter, length, and next we are also calculated quantity of fuel required per year. Since we all know that in hydro there is no fuel, actually the fuel is water and that is actually free, but in diesel we have to pay the price of fuel, and so for that we need to consider the quantity of fuel required per year. So we have also calculated the quantity of diesel, that is our fuel, that will be required per year, quantity of lubricating oil, quantity of water required per year during off peak hours for cooling purposes, quantity of water required per year during peak hours for cooling purposes, and capacity of the pump to regulate the water from the tank to the generator. The design of generator is presented over here: synchronous speed, number of poles, capacity, voltage level, and frequency. All these parameters are given in the table. Next, the costing is also done, that the total fixed cost, total variable cost, total cost, and the cost per kilowatt hour is high, because we know that diesel is the expensive source of power generation. Okay, so we have presented our both design, that is hydro power plant design, and number 2 is diesel power plant design. Okay, so next thing that we have to discuss is the optimization of generating station design according to the 4E. The first method of optimization is peak shaving method. What actually this peak shaving method do? I will this is actually the design load profile number 7. Actually, the peak shaving method suggests that we have to shave the peak. You can see over here, this is the peak time. What if we transfer the load from this time, you can see the time over here. If we transfer this load, that is the actually the peak load, if we transfer this load to here, what it will actually do, it will reduce our maximum demand. If the maximum demand is reduces, what eventually our cost will be decreases, so it will be economical. And nextly, it will also be affect the generating capacity. Our generators would run on the maximum rated capacity. Okay, so that is actually peak shaving method. It will affect the 4 E's, and the major 4 is that it will affect is energy. It will make our system energy efficient by increasing the efficiency of it will make it will make our design the more energy efficient and more economical. Okay, because if we reduce the maximum demand, then eventually it will affect our cost. Okay, the next thing is valley filling method. What actually valley filling method do? Let's consider I have done the peak shaving. I have applied the peak shaving. I have transferred the peak from this time to this time. What is valley filling method is, you can see that in this time the load is actually decreasing, so it will affect the capacity of our generator, that in this duration the generator would run on its low capacity than as compared to its rated capacity. It will decrease the efficiency of our generator. So what valley filling method will suggest that what if we also if we also put some load in this time, not we are not transferring the load from somewhere, but we are also putting the load in this time, so it will also increase our generator efficiency. So that is actually valley filling method. So it will affect the 4 E's in terms of energy, efficiency and economy. The next method is waste heat recovery method, and basically waste heat recovery is the process of heat integration, that is reusing heat energy that would otherwise be disposed of or simply released into the atmosphere, and it is not environmental friendly, that the huge amount of heat and different waste gases are emitted from the power plant. It will affect our environment badly. So what we are actually suggesting it, by recovering waste heat, plants can reduce energy cost and carbon dioxide gas emissions while simultaneously increasing energy efficiency. By employing this method, efficiency and environment will be affected positively. Actually, waste heat method based upon the idea that we can convert this waste heat into some useful heat and use this useful heat for another purposes, like in another industry like sugar industry, in textile industry or any kind of industry. That is actually waste heat recovery method. So that is all from my side, which is the presentation of my project. Now I will let you go through the that is actually appendix number B, which I am telling you earlier, that the design is present over here. We have presented all the designs, all the calculations in appendix, but the results will be summarized over here. Okay, so now I will make you go through the demo of our application and the 3D model. Okay, so this is our design GUI, which I have designed on MATLAB App Designer tool. What we have basically done over here, that this is the home window in which we have put 10 different options for 10 different load profiles, and the 11th option is for the comparisons among the all. Now if I select the load profile number 1, what it will do, it will take me to the window of load profile number 1, where I have calculated all the parameters related to load profile number 1, which I have told previously. There are 4 options. Number 1, technical analysis, in which I have shown average load, peak load, base load, load factor, and energy in kilowatt hour. The next option is load curve. If I select the show load curve button, then what it will do, it will actually plot the load curve of this particular load profile. Okay, so you can see that this is the load curve of this particular load profile. The next option is load duration curve. If I select the button of show load duration curve, what it will actually do, it will plot the load duration curve of that particular load profile. And the last option is economic analysis. Actually, in order to do the economic analysis, we have to know different parameters, that is fixed cost and interest rate, depreciation rate, taxes, insurance, operating cost, maintenance cost, transmission cost. So what we have done is we have done all these detailed calculation for the two cases that we have designed, for which we have designed the power plant. But all the other 8 load profiles, what we have done is we have just simply make the calculator. You can see that if we enter the value over here, enter the fixed cost, enter the semi fixed cost, and enter the running cost, and then if we calculate the button of calculate, it will give me the calculated answer of A and B, which is per kilowatt hour, per kilowatt of maximum demand, and running cost, which is per kilowatt hour of energy generated, and it is the total cost per day, and it is the total cost per kilowatt hour. So that is actually the interface of our GUI. And if we click the, and if I click the button of the home, it will take me back to the it will take me back to this home page which I have shown earlier. This is our home page. Like the load profile 1, I have designed all these 10 load profiles. If I select load profile number 10, it will take me to the load profile number 10 window, and I can able to see all these parameters which I have seen for load profile number 1. Okay, go back to the home page. uh, Next thing is comparison. Okay, so if I click the button of comparison, then it will take me to the window of comparison, where I have plotted the comparative graph of all the load profiles in terms of load factor. You can see that load profile number 1 has a load factor somewhere between 0.6 and 0.7. Actually, it is above 0.65, and you can see that load factor, load profile 2, load profile 3, and load profile 4 and load profile 7 has the lowest load factor among the all. So that is the comparison window, and if I click to the home button, then it will take me to the home window. Okay, so that's all for the demo of load profile analysis, and that is the application designed on App Designer. In order to open the homepage of App Designer, what you need to do is that I am sharing you this document with you, and you just need to open this file, which is pg_cp_home.mlf. If you open, just neglect the other files, it will the all other files are the dependency of this file. These all other files are dependent on this file. This is the main file. If you open this file, then you can actually access all the interface that I have told you. And this is the layout, this is the 3D layout of our hydropower plant. You can see that this is the main gate, and this is the parking area. Let me zoom it. This is HR building. The upper floor is for canteen, and the first floor is for canteen, and the ground floor is for HR. Okay, and this is the warehouse, and these are the vehicles that are to be used inside the power plant. Okay, now let me zoom through the turbine and dams area. So this is the dam, and let me zoom in. These are 4 turbines, 1, 2, 3, and 4. Okay, so these are 4 turbines, and the generator are placed below the turbines. You can see that below the turbines that we have placed 4 generators, one for each turbine. Okay, So this is the layout of our hydropower plant. You can see the transmission system over there, transformer and towers and transmission towers. Okay, so that's all related to the hydropower plant designing. And this is the whole layout of our diesel power plant. This is the main gate. This is the security office. This is the canteen, human resource department, workhouse, warehouse, and generator rooms. Okay. This is the security office. You can see that. So these are basically the generator room in which we have planted the 4 generator. You can see that these are the tanks for the fuel, and the one generator is showing over here. This is the generator, and this is the layout of the generator room. There are also other buildings such as warehouse. Let me zoom it. This is the warehouse, and this is the workshop. This is canteen and the play area, and this building is HR.